So if you remember when we did, oh, that glare is horrible. Sorry, guys. Is that better?
Yes,
Yeah, there you
that's
go.
better.
Remember, everything that we did with concrete came back to strain diagrams, and it came back to Whitney block. Where this was AS, FS, and this was our C sub C, and we did everything like that. Does that vaguely look familiar?
Yeah. Yes.
There's stress, there's strain. This was our distance C, so the block height was A. And then we went through and basically wrote sum of forces X equals 0, and it was minus C sub C plus our TS was all equal to 0 on that guy, right? When we did sum of forces X. And so that's how you came up to find out that that ASFY was equal to 0.85 F prime CB times A. And you had to do some things that we said, oh, the strain was 0.003, and then you always had to find that guy, the epsilon S, right? Yeah. Now I've got Zoom recording this, so I'll post this video up. So if you need to come back and if I go too fast through all of this, but this was kind of the heart of everything that we did back in concrete and singly reinforced. Okay, well, composite construction is done almost exactly the same way. Okay, remember you had to find C, but remember the method changed a little bit in beams when I went and I started playing with something like this, where I had some effective flange width on here, and then this was my B on my web, and then you had all of your other dimensions associated with that. I left off D off of this. Sorry about that. Right. And so then you kind of worked the process here. But do you remember the trick that was involved with the T-beam? There was one extra step that you had to do.
The area.
Well, that is an issue, but it had to do with the strain diagram on here.
No, so I mean, like if it's going to be in the top flange or if it's going to be in the.
Exactly. So if this is, you had two possible strain conditions. So one of them, that's my first one. We could, if depending on the dimensions of this, that's 0.003. I could end up with a case that looked like that, right? Okay. Or I could end up with a case where it did something more like that. Meaning that here, that's my A1. That's my A2, right? And so here, if I call this as the thickness of the slab, which we normally call that as W, here, A1 is less than H is one case, and then A2 is greater than H is the other case for the pictures. And it's only one of them can exist, right? But the difference comes in the Whitney block for this guy. All right, so if I pull this thing down for the first case, scoot that up a little bit. That glare is horrible today. I wonder if I can just take that off. I need a professional lighting mechanism. It's bright out the back window and I can't get the room dark enough to try this. Keep that up. Yes, no. Yeah, it's just. Okay, all right. So remember for the first T-beam case, again, here, then the stress block on this thing looks something kind of like this. Where we call that as an A1. That's your compression in the slab on this. And then what happens is, remember, concrete, we neglect the tension, you're still playing the ASFY game on this guy, right? So it's exactly the same way for the first case. Okay, but what happens if you end up with the second case is now part of that flange and the web both started to factor in. So now your block ended up doing something like this, and it was the A parameter that you're checking against H, not necessarily the C. And I completely misspoke on. I wrote something wrong here. This guy is a C here, right? So for where the neutral axis is located, you're checking if the neutral axis is in the slab versus. I had it right here. I wrote it down wrong there. So what happens here is now you end up with a CC1 there, but you pick up a CC2 here, right? And they were different values because the width was changing on all of these, right? So that's my AS FY on that. Can you see, does that make sense? And how we constructed those should seem kind of. All right. So the first one is no different than what we had back when we did this guy. It's exactly the same. Okay, it was the second one that things changed a little bit. So if I can slide this up a little bit. All right, so for the case where A2 was greater than the thickness of the slab, if I do sum of forces in the X equal to 0 on this thing, then what you got was minus CC1 minus CC2 plus TS all equaled 0, right? And we know that TS is ASFS, which hopefully is ASFY for ductility. We know that CC1 is 0.85 F prime C, times that B effective, the width of the slab that you're using, multiplied by the thickness of the slab, right? That's the full compressive force that can develop in the slab. And then CC2 is 0.85 F prime C. That's times the stem width, BW, and then that's multiplied by A2 minus H. Remember how we did all that?
Yeah.
Yeah. I probably have to do. This method right here is the heart of composite construction in steel and concrete. Except now it changes a little bit, but it's the exact same approach. So for concrete, that's what we did. All right, so let me slide up here, and let's try to apply this idea to what's happening to our concrete slab, or to our all right, so let's call that as effective widths. We'll still call that as our H. Now we have a distance that this is thickness of the flange. This distance is D minus 2 TF. And then that guy is TF for an I-shaped beam. Now, for an irregular shaped steel concrete, then obviously these dimensions change, but the approach is still going to work. All right. And again, we're calling this as that's our D, right? And then, of course, this is thickness of the web. So I'm going to call this as region 1. I'm going to call this as region 2. We'll call the web as region 3. And then we're going to call this guy as region 4. Okay, all right. So what we're going to do is we're going to have now multiple cases, because just like we had in the concrete T-beam, my neutral axis could either be in the slab, it could be in the top flange, it could be in the web, or it could be in the bottom flange. There are 4 cases that you have to analyze on this. Okay, only one of them is going to work. So what we're going to do, if I go and I try to draw my Whitney block corresponding to the first case, which is the case where A is less than H on here, that diagram that we build looks something like this. The concrete block goes to here. That height is A, right? And then, so that gets me our compressive force in the concrete. And then what happens is that whereas in the reinforced concrete case, we neglected tension in concrete, the steel beam, I can't do that, right? And so what's going to happen is you're going to pick up a T2 here, you pick up a T3 here, and you pick up a T4 there, right? Because we just break it into regions, the flange, the web, and the bottom flange. Does that make sense? All right, so
yes.
So C sub C is 0.85 F prime C times our B effective, okay, multiplied by A. Okay. And again, we're going all the way up to the plastic moment on this thing. So T2 and T4 are the same. Those guys are just the, oops, I need one more dimension. The width of this guy is BF. Coming out of the steel tables, BF multiplied by TF is the area of the flange multiplied by the FY of the steel. And then T3 is going to be equal to, what was it, D minus 2TF, and multiplied by the thickness of the web multiplied by FY. So it's the same basic approach that we set up. And so the only unknown in all of this is going to be this little A guy. Okay, for the case where the A is still up in the slab on this case. Now again, you have to know all the distances on this thing, right? This is A over 2. This distance is going to look like what is it?
TF over 2 plus H.
Yeah, H plus TF over 2 gets me this guy. And then you can build these guys all the way down, so forth and so on, right?
And they're always going to act in the middle section.
Yeah, because we're idealizing the AISC beam as being rectangular pieces.
Okay.
So we're going to neglect the fillets on this thing. You know, and so
okay.
I mean, technically it shouldn't, but it doesn't make that much of a difference in the calculation that we're doing. And it's, again, we're just kind of looking for this. So what we're going to do then is to compute the moment capacity of this guy. If this is my case, is I'm going to sum moments at the top of the beam at O, right? And so I can do sum of moments at O is going to be equal to C sub C times A over 2. Okay. And that, if I go this way positive relative to that, this is a minus plus T2 times H plus TF over 2 plus T3, which is going to be what? H plus TF plus 1/2 of D minus 2TF on those, plus then T4, which is H plus TF plus D minus 2TF plus TF over 2. I don't think I made any math errors on that, but you guys get the idea of what we're doing.
Mm-hmm.
I'm just picking those off, and that's how you get the moment capacity. So if you can prove that this guy is the right case, then these are all the equations that you need. Right? So I can use this thing to solve for A equals whatever that equation is, just by doing the algebra on it, right? Which came out of playing with these equations, right?
Yes.
Okay. So basically, you'll run all these numbers and you'll pick off whatever. I lost a. Sorry, I'm gonna go ahead and write. I'm gonna write the first one out for you just so you can see it because it's the same process. Sum of forces x equals 0. This way, positive. We said so. This thing is going to be minus c sub c plus t2 plus t3 plus t4, all equal to 0, and then you plug in the parts that go to that. And so out of this, we solve for A. And so if the logic on this is if A is less than H, okay, then you've met your assumption. This is true. If not, then you have to go through and proceed to the next one. And this is where it gets a little squirrely. Let me find some more paper real quick. Any questions on what we've done so far? All right, so we can do case 2, and I'm only going to work the first 2 cases because once you understand this one, then the others are just the exact same process. All right, we call that as H. Okay, now this case, it's a lot of lines, but it's the same basic approach. Okay, now we're in the case where my A is greater than H, but it's less than H plus TF. Because this distance we said was TF, and that distance is what we're calling as A, where the block is going to be. So it comes out of the... And the thing that's kind of cool about this is I don't even really have to play with the strain diagrams on this. I'm just going straight to Whitney and knocking these things out. So if I go through and I do that, then what happens is I pick up, I have a C1 value that's there. This chunk right here gets me, what would be a C2, which is basically the compression that's in the top part of the flange that's here. Right? And then if I bring this guy across, I pick up a T2, that's my T2 this time, and then I get my T3, and then I get my T4, and we play the same game. So C1 is now 0.85 F prime C B effective times H, because again, that was the flange width on this. C2 now is 0.85 F prime C. It's the width of the flange, and then multiplied by A minus H, because that's what's left of the compression block. Okay, and I lied on that. That's not right. Let's fix it. What was the mistake I made?
Well, I don't know what you wrote because you just erased it.
Well, that's good.
It's not concrete anymore.
It's not concrete anymore, exactly. So what we have is it's going to be the area of the flange, which is BF times A minus H multiplied by FY. Because now you're into steel. So this guy is the concrete, and then everything else that we're getting ready to do is going to be steel. So you got to watch the FY versus the 0.85 F prime C. All right. T2, what's T2's value?
Is it just ASFY?
Same as before?
Well, but the problem is you've claimed part of it for compression. So now we got to figure out what's the area of this guy.
So it's going to be TF minus A minus H.
TF minus A. I'm gonna write it a different way just so I can see it. I'm gonna do H plus TF minus A.
Yeah.
Okay, you're on the right track, Guillermo. I think you would have had a sign problem on it, and then I'm gonna multiply that by Fy, right? And then T3 is going to end up being just the same as what we had before, D minus 2TF multiplied by Fy, and then T4 is still the same thing, BF times TF, and what did I miss something on T3? What did I miss?
The H.
Whoops. Actually, both of them I missed. I need a BF on this guy times Fy. I need a TW on this guy, but left off the width on all of them, and then that's Fy. We'll get you those. Okay. And when you do that, if you notice, there's only, how many unknowns do you have in this, assuming you know all the section properties?
Just the A.
Just the A again. It's the same problem. It's just the equation changes a little bit. All right, so if I do sum of forces X equals 0 to the right, positive, now I have minus C1 minus C2 plus T2 plus T3 plus T4. I don't know why I labeled it 2, 3, and 4, but you get it. And it's the same, it's the exact same game. Okay, and so what we're going to do is we're going to solve. You're going to solve for A again. And then once I do that, then I can go in and I can play the exact same game with, well, that distance we know is A over 2. This guy is now H plus A minus H divided by 2. And you can build all of these the exact same way. Start picking off those distances that I know, because I know from the bottom of this to the bottom of this, I know that dimension right there has to be A.
Yeah.
And so T2 is at the center of what's left of this. So that formula gets long, but once you have A, it's easy. It'll all fall out for you pretty quickly, right?
Yes.
Are you seeing the pattern on how this is set up? It's not overly complex. If you understand Whitney, this is super, super easy. All right.
Yeah, makes sense.
Okay. Case 3, I'm just going to draw the picture for case 3.
So does it go down into the web?
And that's what case 3 is. And so now, if I call this distance, this was what, H plus TF.
You're a bit off the screen now.
I'm getting too close to the edge, aren't I? Sorry.
Thanks, man. I was about to say it.
And I'm also writing kind of small, which doesn't help things. H TF. Okay, so case 3 then is the case where H plus TF is less than A is less than H plus TF plus D minus 2TF, right? Which is our definition of zone 3. Right. So what's the diagram look like? That's my slab. This is my flange. You know, if I say that this is my A, I'm drawing the picture a little bigger so you guys can see it. So that goes to here. This goes to here. All right. So compressive block now is this. This guy is in compression, and then this guy becomes a compressive piece, and then I'm left off a line, didn't I? Comes across there. All right, so same thing. C1, C2, C3. This is what's left of T3, and this is T4.
So So now we leave out T2 because all the steel is just in compression, right?
Correct. Correct.
Okay.
Right. So C1 is the same, 0.85. F prime C B effective gets me that guy times H. C2 now is Fy, the stress, multiplied by the flange width, multiplied by the full flange height, Tf. And then C3 is where it gets a little squirrely, right? Fy times Tw times what would be A minus H plus Tf, right? It's what's left of the A block that you haven't already complained or gathered. All right, and then T3, if we do that, this one gets a little, you can see the algebraic formulas of these get a little bit long, but it's basically, I'm going to find what's left of, I have to find this height, which you can do just like we've done before. So it's what, H plus Tf plus this A minus H plus Tf value. You can see the equations start getting kind of long, but it's not overly difficult. Okay. And most of the time, that's as far as you have to go. For I-beams, W shapes, and S shapes, generally it's either case 1, case 2, or case 3. If you had some really bizarre, disproportionate, steel shape that was custom, custom made that looked something that, if I did something really, really stupid that looked like this, and a little bitty guy, and a little bitty guy, and then a slab that looked like that, I could pull that thing all the way down into the bottom, but it doesn't happen on most standard shapes very often. But the construction technique is exactly the same. Does that seem logical?
And can you think of a situation where that would ever happen? Is that like a bridge girder kind of situation? Or?
I've never come across it in practice. It's more of a theoretical exercise in graduate school, so that you're aware of it. I mean, I guess because the hardest part about composite construction, and the thing that we haven't really talked a lot about, is the whole reason that we're doing all of this. All right, if I go back to, let's just say go back to case 1 on this, which was the slab, everything was up here, and we had, okay, the one thing that we haven't talked about is that there has to be some sort of connection between those two guys, which is the headed studs or something like that, or welded bars, or what happens. And so we have to be able to design these guys. And the reason we have to go through all of this is I have to know the force that acts at that interface. All right? So what we do is we come in and we say, all right, if this is, if we said that we had some block that this guy was C1 and I cut the stud off of this thing here, then there has to be some sort of, it's a shear across that stud. They call it Q most of the time. I'm not quite sure why. Okay. Is this, and then if I look at the top of the beam with what I just cut, I would get the opposite Q there, and then this would be my T2, this would be my T3, and this would be my T4. Right, and so this is for the case where A was less than H. Does that make sense?
Yes.
All I did is I cut the stud and separated it into two pieces, but my forces have to stay the same to what we had before. So in this case, if I do sum of forces X on this guy, I know that C1 is equal to Q. Right? And this is the Q ends up being the number of studs multiplied by the capacity of one stud. The shear capacity of one stud. All right, so if you know that stud's worth, 4 kips per stud, based on the size and the grade of steel that you chose, then all I do is take the number of studs that I needed, that I had, and I multiply it by that value, and I set it equal to Q. And you got to make sure then that pretty much what you want from a design standpoint, we want Q greater than C1. right? Because that means that this connection is effective, and when that happens, this is what we call as fully composite. Okay, it means that you've done the construction in such a way that the slab and the beam are both contributing to the flexural capacity.
So does this mean that a case one is preferable at all times?
Generally, pretty much always, that's what we design things for, is fully composite. But again, in grad school, you guys are going to see an exercise where they're going to go to some theoretical. Well, what if I don't put enough studs in here? What happens to this thing, right? And so what happens in this picture, and I'll show you real quick. Right now, the strain diagram looks something kind of like this, depending on, it's all uniform, everything's working together in one piece, right? What would happen to this diagram if I didn't have any studs at all? That they weren't working together. Well, it changes a little bit. And this is what we call the non-composite case. All right, and I do this. That basically, the slab does his own thing, okay, and then the beam does its own thing. And that becomes your strain diagram, and it basically becomes broken on this. So what the studs are doing is, if you look at this line that's right here, at the same location it was here, the studs are forcing this thing to go back in to form this guy. Right? So that's the difference. And so you can, depending on how many studs I give, I can, the more studs I put in, the more I start to squeeze this line in, and it starts, if I put enough studs in, I can get back to here, but that becomes the strain case. It becomes a whole lot more complex, and we're not doing that in this class, but that's the idea of what we're doing. I'm going to have you guys look at non-composite case. I'm going to have you guys look at the fully composite case, which was this one. Does that make sense?
Yes.
I threw a lot at you, I know. So for this one actually gets kind of interesting, because now you know the slab that the slab, you'd have, the tension of steel in the slab, I would have my CS, and then on the beam, what happens is this guy splits down the middle. So this is the neutral axis of the beam, that you would end up with a C in the flange, a C in the web, a tension in the web, and a tension in the flange. Okay, and then you would turn all that in to find the moment capacity of the beam. And you do all of this, and you find the moment capacity of the slab. And all I'm going to do is add those two guys together. Okay. The beam becomes really, really easy because it's symmetrical, right? It's basically Zx times Fy. If you remember how we formulated the plastic section modules, it came out of a diagram that looked exactly like this. But that's the approach that we're going to kind of chew on and we're going to play with. Okay? Questions, thoughts on that?
Would the non-composite case be preferable in like a seismic scenario?
Why do you say that? I won't say no, but I'm wondering what your thinking is.
I'm just thinking, something that's less rigid, less likely to break, something that you might be able to move relative to each other without.
Yeah, the only problem is that this guy, his capacity is going to be so much less than this. Okay. All right. One of the things that makes this guy a little bit more complex, actually makes both of them more complex, is something known as shored construction. And this is the reason I was asking, is that if I count on the slab doing some of the work on this, I have to hold this beam up in place until the concrete hardens. I have to provide bracing underneath it, right?
Yeah.
Because otherwise, if I go and I pour all this wet concrete onto a beam that's already in place, this beam's going to respond to the load. The beam will carry not only his own load, but he'll also carry the load of the slab on him. Okay, but if I shore it, then the slab carries its weight, the beam carries its own weight, and then when I let off the shoring, the vertical loads are going to be applied to both. So
Gotcha.
yeah, so that's a bit of a trick, and again, we're not going to worry about that too much in this class, but you'll hear that term shored construction or unshored construction will start to kind of tip us into that as well. But otherwise, it's the same mechanics approach. Once you figure out the case that you have, this C1 equals Q case is always true for the shear studs. Once I have the compression force in the slab, I know what Q needs to be, because everything else is happening down below. Because if the neutral axis dipped down on the other case, it was what we had. We had a little bit of a CF guy, we had a TF, and then we had T3, and then we had T4, right? That was the only difference of these diagrams, as I went from case 1 through 2 into 3, right? On the previous pages. So that's kind of the basics of what we're looking at on that. So the way that I would set this up, and the way that I did my spreadsheet on this thing, okay, is I had all my section properties here, okay, and then all I did is I tallied all 4 of these formulas for case 1. I did case 2. I just did them all side by side. I ran them all in my spreadsheet because I was going to have to do it anyway. In case 4, 3, like that, and then of course I ran out of room. There should be a case 4 also. All right, and when you do this, somewhere in here, you're going to calculate an A. A equals this, A equals this, A equals this, A equals this for the cases to be true, right? Only one of the 4 can happen. So you just kind of do a logic check, over in some lines over here that says, hey, A is less than H. If that's true, it's case 1. If H plus TF is less than, if H is less than A is less than A plus, golly, sorry guys, H plus TF, then I know that's case 2. And so on and so forth. And so you just basically take the A value down here and compare it against these hard numbers that you know based on the dimensions of this thing, and you'll know exactly which one it is. Let me go see if I can pull mine up real quick. Does that kind of make sense?
Yeah.
I'm logging into OneDrive here. Oops. Same one. Crap. If I do the stop the share, I'm going to share a different screen now. Can you guys see that?
Yes.
I figure out how to zoom. So all you can see is that I went through and did my section properties that are here. Here are the dimensions that I set. And I didn't necessarily I didn't even set it to an AISC shape. I just said, what's my slab thickness? What's my top flange thickness? What's my web? What's my bottom flange thickness? And so here are all the widths. Here are all the thicknesses according to, and then I compute the A's, of course. And then basically I run through this thing, and you can see, here's my case 1. Is the plastic neutral axis in the slab. This is the A less than H case. And I run through and I calculate CC, the tension in the flange, the tension in the web, the tension in the bottom. I even go through and do, and then I figure out what my C total is and and so forth and so on. Once I have that, then I can figure out their locations by just doing those calculations off of, because the position of these are the dimensions of where those forces are measured from the top of the beam, right? And so somewhere, where's my A at? I have the beam data in there. Oh, this guy right here. There's where I computed A. And you can see it's just that simple formula for case 1, right?
Mm-hmm.
And then if I go over and I do this, I didn't even do the bottom case on this one. I just did the top 3, but it's the same basic approach. And all you're doing is the blocks look exactly the same, with the exception that in case 2, now that plastic neutral axis is down in the top flange of your beam, right? So now I've got a C sub C. I have a CFT that's on here, okay? And then the one thing I had to do is I had to split this guy. So see, this part right here changes a little bit from what I had over here. Does that make sense?
Yeah.
Yep. And then I went through and I did the same thing on the next one, and you did the same thing on the next one. And what happens is in all of these, is that the A that I calculated on this, we found out it was 1.64 inches. And if you go back and look over here, I said my slab thickness was 5 inches. So I knew that it was in this one. So that's why it went highlighted green. If I change this to like a 1, did some conditional formatting, then it went over and it figured out where that A had to be able to make the calculations work. Does that make sense? That's all I'm looking for, is you guys to be able to generate something like this. Because if you can make this spreadsheet, then you'll understand you understand the mechanics of not only concrete, but you also understand the mechanics behind composite construction. And so this is my fully composite sheet, the way that I worked it out. And somewhere, where's my A at? Yeah, so this dimension is kind of the A, but I took it from the top of the top flange, so I kind of worked off of it a little bit differently. So, but it's however you want to set that thing up, But this is basically my estimate on A. It's A. This is actually A minus H, and this guy is A minus H minus TF on those. And so if you write it this way, if the number goes negative on you, you know it can't be true, because it meant that it's above the section that you're looking at. I basically dropped zone by zone by zone on this. Okay, and then obviously this is greater than the 1 inch that I made, but it's a really cool spreadsheet. And then all you do is, once it goes green, and you know that, oh, now I can go do my moment capacity calculation, which is done the exact same way on all parts, and you're in business. You know exactly what the moment is when the slab works that way. And then you can go to the next step and start figuring out, rebar size in the slab or whatnot. But this is just the basic Whitney block calculator that I made. It's really, really handy. Does that work?
Yeah.
Okay.
That's impressive.
So, like I say, once you have it, the hardest part is getting the algebra worked out, and I just did all 3 of them for you. But it'll take you a little bit of chewing on. I want you guys to try to put it together. This should be video. I think the video is still running on my Zoom session, and if it is, if I stop my share. Oh, did I not? Oh, you got to be kidding me! I didn't record it. Son of a gun. I'll send you the notes. How's that?
I'm gonna say that's okay. That's like 3-4 pages of notes, so I think we should be good.
I'll scan the notes. I fully meant to record all of that for you. Maybe
As
the
you
first
mentioned,
one.
it's like concrete.
It's exactly like concrete.
One
Yeah,
extra step. Yeah.
That would have been a great one to have on video. I'm sorry, guys. I thought I hit it and I didn't. So.
That's fine.
So, all right, but that's the nature of what we're looking for. So, any questions on that? It's really not that long of an assignment once you understand the algebra and the derivation. So, you guys definitely have an advantage over Justin and Austin, because without this, they're gonna have no idea what to do.
So I can guarantee I will have some questions come Wednesday.
Okay. So let's plan on touching base on Wednesday on that. And then you should be able to run through it. But that's the way I would set this thing up. Is just, it's a handy enough calculator. I use it from time to time just to kind of get a real quick idea of how much capacity this thing is worth total. You know, again, it's not 100% theoretically correct, but it's a good first guesstimate, if you will,
First guess.
Yeah.
to get you going. So, and then once you have that, then you can go and do some more advanced methods for analysis. But it's just for, like I say, for just kind of understanding the mechanics and how it all works. I think it does a real good job of illustrating the you know, how the free body diagram changes depending on the case that you're in. And that's kind of what I want you guys getting out of this.
Gotcha.
Okay, all right. Oh, that's aggravating. I didn't record that. I know I hit it. I'll put this up on, you know, up on YouTube, let you guys have it, and you can go back at your leisure and blah. Okay, all right. Well, it is what it is at this point, so. All right.
Yeah.
That's
All right.
fine.
I know we went really long. Went over our 40 minutes. I went ahead and bought the upgraded Zoom license so that we can go as long as we want now.
I was gonna ask about that. I thought you might have.
Yeah. So anyway, that's what we got. So, alrighty.
Perfect.
All right.
All right, guys.
Yes.
Holler at me if you got questions. Otherwise, I'll plan on meeting you all on Wednesday.
All right.
That sounds
Second.
good.
Okay. All right, guys. All right.
Thank you so
Thanks,
much.
John.
See ya.
All right, bye.
See ya.